All right, welcome back to another video, everyone. This one we're breaking down a question from last year's exam 1. So we need to try and answer this one without using a calculator. So off the bat, we've been given a function. This function has been written in function notation. So we can see here the name of this function is f. We're going from a domain of R to a codomain of R. And just remember, this is always going to be equal to R for the purpose of methods. So just remember, you don't have to write anything else except for R for this second one here. The part that we need to pay attention to is just the domain is all of the real numbers. So there's no domain restrictions on this particular function. And the function has the rule, which is written over here, which is a polynomial function, and specifically it's a cubic function. So the first question is we want to verify that x equals 0 is a solution of f of x equals 0. So basically, if we see this kind of phrasing, a solution of basically just means if we substitute x equals 5 into this particular equation, we should get out a value of 0. So what we need to do to check that is we're just going to use our substitution skills, and we're going to replace the rule for this function f with an input of 5. So if we go ahead and do that, the equation becomes 5 cubed minus 5 squared minus 16 times 5 minus 20. And going down and resolving that, we get 125 minus 25 minus 80 minus 20. And yes, you would need to do 16 times 5 in your head without using a calculator. I guess if we want to verify how to do that, we can just set up our multiplication like this. 5 times 6 is 30. 5 times 10 is equal to 50. And then we can just go ahead and add those two together to get our answer of 80. That's just a quick recap of that, but you would need to do this by hand. And then once you get this expression, you can just verify for yourself. That's 125 minus 25, so that gives us 100 minus 80. That's 20 minus 20. We get 0. So that's verifying this solution. All right, so next up, we need to express f of x in this particular form here. So in order to answer this question, we're going to need to use some polynomial long division. What we know so far, based on part A, is that f with an input of 5 is equal to 0. We can therefore say that based on a couple of theorems, first up, the factor theorem, which states that when we have a polynomial, we put in an input of x, and we get out an output of 0. That tells us, I should have said the first one, based on the remainder theorem, the input that we get out with the function is the remainder after polynomial long division. And the factor theorem states that if that remainder is equal to 0, the thing that we put in there is a factor. So all of that is to say 5 is a factor. So 5 is a factor of f of x. And also we can say that because 5 is a factor of x, therefore x, or let's just say f of x divides by x minus 5 with remainder 0. So why is it x minus 5? Well, if we think about this x minus 5 factor, if I was to substitute in 5 here, we're going to get out an output of 5 minus 5 for this particular linear thing. And if we multiply by that, that's 0. We multiply by 0, we get 0. We can also see that that's a factor because it's being written for us here. So all of that is to say we need to use some form of division. So we can either choose, we could use polynomial long division, we can use synthetic division, or we could use equating coefficients method. I personally think that synthetic division is the easiest option here. The way synthetic division works is we're just going to go ahead and write out the coefficients of f of x, which here are 1, -1, -16, and -20. We'll just write them down here. So we have 1, -1, -16, -20, and that's written, so we're writing those coefficients in descending powers of x order. We then make this little square shape like this, and we chuck our 5 over here, so that's the factor that we're dividing by, and we just do this procedure where first up we drop down that 1, down here, that only works if this is a monic quadratic, monic polynomial. So we can see that, for example, what we're doing here is we're doing x cubed divided by x is just going to get us out a factor of 1 in this sort of factorization over here. In this case, yeah, if it's monic, you don't have to worry about anything else there. Then we just do 5 times 1, that gives us 5. Oh, sorry about that. So equals 5 over here. So that was 5 times 1. That gives us 5. Then we do -1 plus 5, which gives us 4. Then we do 5 times 4, which gives us 20. -16 plus 20 gives us 4. And then lastly, we have 5 times 4 over like this. And that spits out an answer of 20, so positive 20, negative 20 plus 20 is equal to 0, and that last number there is our remainder. So as we can see, the remainder is in fact 0, which means that we've done this procedure correctly, and those other 3 numbers there are the coefficients of our quadratic factor. So that's just telling us that f of x can be written as x minus 5 times x squared plus 4x plus 4. So we're writing those in descending, those coefficients there. We're attaching them to powers of x in descending power, counting down from 2. Lastly, we want to fully factorize it because we want to write it in this form here. And we can see, okay, we want to factorize a quadratic. We can see we want to find 2 numbers that add to make 4 and multiply to make 4. So those 2 numbers are going to be 2 and 2, which means that we can factorize this as x minus 4, x plus 2 squared. And therefore, we can see that if we're wanting to write it in this form, we can say that d is equal to 2 in the way that it's been written there. And that's allowed us to factorize that fully. All right, let's jump forward and look at the next one. All right, so here we have a graph of f of x shown below. And basically all we have to do here is label all of the coordinate pairs of the intercepts for this particular function. So the couple of things that you need to know about this one here. So first up, f is a cubic polynomial, which basically means it's going to have ends which start like this and end like this. This is always going to be true for any odd-powered polynomial where the coefficient in front of the leading power of x, in this case the leading power of x is x cubed. Whenever that's positive, that'll be the case. Now, if you have a case where f of x is equal to, say, negative x cubed, in that case we're going to have the 2 endpoints going down and down. So if we hadn't been given this sketch, we could work out it's going to look like this and this. We've also got these 2 factors. So we can see the 2 factors here are f of 5 is going to spit out 0 and f of -2 is going to spit out 0. So those are our 2 x-intercepts basically. And from that alone, we should be able to work out that this first one is going to be -2 and this second one is going to be equal to 5. But more specifically, if we hadn't been given the skeleton of this graph, we'd be able to work out that this one is going to be like a touch and turn sort of factor. So a quadratic factor where it hits this and then it goes down. That's because f of x is equal to x plus 2 squared, x minus 1, and that, like from the previous question, and that has this square factor next to it, so it's quadratic. Lastly, we just need to work out what this y-intercept is. So that's basically if I put in an input of 0, what's the output for y there? So we could do that here. We could sub in 0, do 2 squared times -5, but we could also just go back up here to the start. So the question here is written for us in fully expanded form. So we can see if I put in x equals 0 into this function here, that's going to cancel, that's going to cancel, that's going to cancel. We'll just be left with -20 as our factor, sorry, as our y-intercept here. So that's an answer of -20 there. All right, so moving on. Now we've been given a new function. So this function is g of x. And we're doing something with this equation y equals f of x times g of x. So let's just work out what that equation is. Now, based on the previous question, f of x is equal to x plus 2 squared times x minus 5. And we're actually multiplying that by this new g function, which is x plus 2. So we're timesing it by x plus 2. Now we can see that just creates a new polynomial, which is x plus 2 cubed times x minus 5. So now let's read the question and work out what it's asking. So we want to state the coordinates of the stationary point of inflection of this particular graph. So we can see here, we've now modified this graph. We've got a new polynomial, and in this particular case, this new polynomial, once again, it still has two roots, so two values of x for which y is equal to 0, or in other words, two x-intercepts. One of them is still at -2, one of them's at 5. The only difference here is that now this is actually a quartic polynomial, because if I expand this out, you can see this leading term is going to be x cubed, and that's going to times by x to get an x to the power of 4 factor. And the thing that we need to know about, even powers of x when we're dealing with polynomials is, if you think about a quadratic polynomial, we get this parabola shape where it goes like this. We'd call this like concave up. The same is actually true for any even powers of x. So we know that the two sort of ends are going to look like this and like this for this particular quartic. All we need to do is work out what happens in the middle. So what's going to happen here is, it's going to go down to this thing here, which we can see is a cubic factor. So it's going to go down like this. So it's like a stationary point of inflection sort of situation. And then it might go down like this, and then we know it's going to come back up over here. I don't know if that's what it looks like, but it's going to kind of follow this pattern where it goes down. It makes this stationary point of inflection, which is essentially where the graph changes concavity from being concave up over here to being concave down over here. So that's our stationary point of inflection, and then it goes up like that. So in this first question, we just need to state the coordinates of the stationary point of inflection. And as I said, that's just going to be stationary point of inflection. It's just going to occur at the coordinates -2, 0, as we can see from this depiction here. That's like the concave up to concave down pattern. And we want to write the values of x for which this function is greater than or equal to 0. So if we have a look at this drawing that I've done up here, we can see that this function is going to be greater than or equal to 0 for all of the values of x below this point here. That red line is above the x-axis, so everywhere over here, and also for all of the values of x that are above this point over here. So how do we describe that? Well, that first line over there is all of the x values, so x is an element of all of the x values up to and including -2. Why is it including -2? Because we've got this greater than or equal to 0. So when x is equal to -2, that's a y value of 0, so it looks like this. And we want to say all of those values, and also all of the ones over here. Now, the way that we say "and also" in maths is actually using an "or" symbol, or union with. So we're going to say all of those ones, and also these ones up here, which is basically from 5 up to infinity. If you were to say "and," which you might be tempted to do, so this symbol here means "and," that's actually wrong. So that "and" symbol means something that satisfies both of these two conditions. So in this case, there are no numbers that are between -infinity and -2, and also 5 to infinity. So I guess, yeah, a more mathematically accurate way of reading this statement that I've written here is from -infinity to -2, or 5 to infinity. This overall function that we can see here is going to get out an output of 0 or more. All right, so hopefully that little explanation made sense. The notation here is super important. So I've written this one here using interval notation, but just for argument's sake, another equally valid way that you could write this is you could say all of the x's such that x is, say, for example, you could say like from negative infinity. Let's say like all of the x's where x is less than or equal to -2, and also, or union with, or all of the x's where x is greater than or equal to 5. You could say something like that if you want to use set notations. That's these weird curly brackets you could write a statement like that. So there are a couple of options for how you can express that. But of course, if you use this symbol, that would be wrong. And if you got these inequality signs the wrong way, that would be wrong. And if you only included like half of this, that would also be wrong. So it is important that you read it accurately and also know how to interpret this symbol here as greater than or equal to 0. So the crocodile's eating the larger number. Yeah, all right. So hopefully that little video helped you. That's a question from last year's exam. Next week, I might give you a tech active one to practice those CAS calculator skills. I'll see you guys in class. Have a good one.